that we will analyze the remainder of his results, all that in the next half an hour, and then we will all sit here, the 3 lectures this week. Or is it 4? Whoever is in the room, and we will try to answer your questions. What does that sound? Okay.
Okay, thank you. I will try to limit this to a half hour, so we have time for more fun things.
35 minutes.
So last time I mentioned some constructions of 2D CFTs, such as Narang lattice compactification, which describe some general class of theories that could be thought of analog of free bosons that are perfectly unitary 2D conformal field theories. Then we have this orbifold construction. We have some CFT with some symmetry, discrete symmetry G. We can gauge it, and typically, if the action of the group is asymmetric on the holomorphic and anti-holomorphic side, there could be potential 't Hooft anomaly. But if the 't Hooft anomaly is absent, this can be consistently and unambiguously constructed. And then there are WZW and coset models. These are based on some. You can start with some WZW model, which can either be described in terms of representations of current algebra, or you can view this as a nonlinear signal model on a Lie group with some H flux turned on, and then you can gauge a subgroup of that. The coset model. So, I mean, if you want to describe this in the Lagrangian language, you can write it down, but it's not obvious that this would be some exactly solvable conformal field theory. It turns out that there is a set of technique that allows one to directly build the exact operator spectrum in such models, and in such a way that the theory is going to be marginally invariant and satisfy all the consistency condition of a CFT. Some special case of the coset model, in fact, reproduces the minimal models. And now, in general, if you want to demand a CFT is unitary, the WZM model would require the group G to be a semi-simple Lie group. From the point of view of Lie algebra, you demand a positive definite inner product on the Lie algebra. Now, it turns out that there are coset constructions where G is non-compact, so the WZM model by itself would have been non-unitary, but the gauged version is actually unitary. So an example of this is so-called cigar theory. There's some we call SL2 mod U1 cigar model that describes some nonlinear signal model on the geometry that looks like a cigar with some non-trivial dilettante profile. So that would be an example of a non-compact but unitary conformal field theory. It's a little similar to Liouville theory that I discussed. Okay, so at least in the case when G and H are both compact, this actually falls into the class of rational conformal field theories. And as I mentioned last time, this have the property that there's typically some extended holomorphic, or sometimes called chiral vertex algebra. That just means that we have not just operators like the stress and the tensor, but there could be some other currents which are holomorphic with some higher spin possibly, or spin y in the case of current algebra, and generate a bigger vertex algebra. And there are finitely many irreducible representations, finitely many irreps of this holomorphic vertex algebra. And these theories have the property that the weights H and H tilde are supposed to be rational numbers, and so is the central charge. Now, this was a subject of intense study in the 80s, and it was once thought that perhaps all CFTs can be approximated by rational CFTs. That's no longer believed to be the case. In fact, it's believed to be far from the case. And furthermore, in fact, all the known examples of rational CFTs, as far as I know, are constructed either from coset or from the Narain lattice and their orbifolds. So even though in principle there might be a much bigger class of such theories, there are no actual examples beyond these constructions. Okay, now I should emphasize that the rational CFTs are actually quite special in that they always have this extended holomorphic vertex algebra, except the minimal models. The minimal models, the algebra is just the Virasoro algebra, and that's the example of rational CFT. There are finitely many Virasoro primaries. But if you take C to be greater than or equal to 1, you can never have finitely many Virasoro primaries. And the rational CFT will necessarily involve some extra bigger algebra, which implies in particular that there are extra conserved holomorphic currents. Yes? Okay, I'll come to that in just a second. But supersymmetry is an example of this, because you have an extended vertex algebra beyond Virasoro. Now, no. They're not necessarily rational because this is a necessary but not sufficient condition. Importantly, there has to be finitely many irreps. And that's certainly not true for generic superconformal theories. It's true for superconformal minimal models, but it's not true more generally. So I'll come to that. So this is by no means the exhaustive list, of course. So I'll describe some other constructions or attempts of constructions of 2D CFTs. So one can take nonlinear signal model. That seems to be the obvious thing to try, because from Lagrangian point of view, if you have some set of scalar fields, you can, of course, in 2 dimensions, so let's call this maybe M, doesn't matter, J, some Jij phi. So you can write a action like so. In fact, let me write this as capital G. And in fact, instead of phi, let me call it X. These are the fields in a nonlinear signal model. And just to covariantize things, maybe I put the square root G like this. Now this action is classically marginal, and you might imagine that if you choose the Jij appropriately, this will describe perhaps the conformal field theory. Now, if you want to do this, there are other terms you can write down which are also classically marginal, and from the Wilsonian point of view, you may want to consider all of them simultaneously. There are things like Bij x epsilon AB partial A xi partial B xj, where Bij is antisymmetric in ij, and this already shows up in the WZL model, nonlinear signal model description. And then there are non-trivial dilettante terms you can write down, like so, which sometimes is needed to make the theory conformally invariant. It turns out that for general curved target space, well, this term, I guess you can try to kill it by imposing parity symmetry, but this term generally will be generated. And of course, there are infinitely many scalar potential terms that could be generated under RG that are relevant. All of them are relevant. So there are infinitely many relevant operators. So from the Wilsonian point of view, it's actually kind of hard to imagine how you can describe a conformal fixed point from a nonlinear signal model like this. Now, of course, if the target space metric is flat, the theory is free, say torus. We know that such models exist. Such conformal field theories exist. But beyond that, it's hard to establish examples of exact conformal field theory. On the other hand, of course, we know that there are examples like this that involve curved target space. For example, the WZL model themselves are examples like this with non-trivial B field, Bij. And even if you forbid this term, there are other examples, such as the coset model. You take, say, SU2 mod U1 or this SL2 mod U1. In both cases, actually, there are Lagrangian descriptions of these coset models that precisely involve some curved target space and some non-trivial dilettante profile. So these things exist, but we don't really understand very well, in general, to what extent these give rise to CFTs. In particular, in both of these examples, the target space actually are non-compact. This is called the cigar. This is sometimes called the bell geometry. Anyway, I will not write that in detail. And so you might know the statement that if you have a Calabi-Yau manifold, it's about nonlinear sigma model on Calabi-Yau manifold is supposed to give rise to CFT. That is supposed to work in the supersymmetric case. In the bosonic case, the situation is not so clear. As far as I know, there's not really a very clear argument either for or against the existence of a non-trivial nonlinear sigma model on the Calabi-Yau target space. Because, roughly speaking, because it requires some infinite amount of fine-tuning. In the supersymmetric case, there are robust arguments that establish the existence of those CFTs. So at least to me, whether a nonlinear sigma model in the bosonic case can give rise to non-trivial CFTs that are not, either free theory or some of these known non-compact examples, it seems to be still an open question. Rather surprisingly, something so basic that that we don't know the answer to. Yes, but the question is, so I can pose the following question. Does the solution, do those equations on the compact manifold have admit solutions? I mean, we know that there should be topological obstructions, such as first-term class. But even with that satisfied, are there solutions? That is far from obvious. No, leading order is fine, but leading order is not enough. That's what I'm saying. That's what I'm saying. So in the supersymmetric case, you can make arguments either based on space-time supersymmetry or based on worksheet arguments to argue that. Well, the simple way to say this in the supersymmetric case, this will be killed. This scalar, this relevant deformation will be forbidden by supersymmetry, but not in the bosonic case. So it's a rather subtle question. It's not obvious. In fact, there are some arguments against this. For example, if you, they're not really argument, but there are kind of evidences against it. For example, if you consider T4 mod Z2 as an orbital CFT is a perfectly well-defined theory, and want to think of this as a limit of K3 surface. In the supersymmetric case, it makes perfect sense because this supersymmetric CFT has a marginal twist field, which gives rise to the deformation that blows up the orbital fixed point, leads to a smooth K3. In the bosonic case, that's not marginal. So you cannot possibly connect this to a family of K3 nonlinear sigma models that are bosonic. But maybe such family exists. You can just never reach the orbital point. I don't know. Yeah. So anyway, the status of bosonic nonlinear sigma model is not very clear to me. Okay, so now let's say a few words about superconformal field theories. Now, there are different kinds of superconformal algebra. So we have, let's say, n, m superconformal algebra. The n and m, usually in this notation, represent the number of spin 3/2 conserved currents, super currents on the holomorphic and anti-holomorphic sector. We can have 1, 1, 2, 2, 0, and so forth, various possibilities. And these superconformal algebras are not completely specified by the number of supercurrents. And I'll just discuss, just briefly mention two classes of examples, nice examples. One class is 2, 2 superconformal field theory. These have, on the left and on the right, the so-called n equals 2 superconformal algebra. I won't spend time explaining to you the details of this due to lack of time. I just want to point out a few features. So there are abundant examples of 2, 2 superconformal field theory. For example, the supersymmetric nonlinear sigma model on a Calabi-Yau manifold, say M, of complex, let's say real dimension 2D leads to a C equals 3D, C and C tilde equals 3D, 2, 2 superconformal field theory. In fact, these Calabi-Yau models are somewhat special. So it turns out that the n equals 2 superconformal algebra admits an outer automorphism known as the spectral flow. Now, that spectral flow may or may not be a symmetry of the CFT. For the Calabi-Yau models, they happen to be symmetries of the CFT, but generally they may not be. So with spectral flow, this is called the extended n equals 2 superconformal algebra, which controls the Calabi-Yau models. But there are many, many other examples of 2,2 theories that do not admit spectral flow symmetries. A reason why there are abundant examples of 2,2 superconformal field theories is that in this case, a essential property is that marginal deformations these marginal deformations are deformations that, to leading order in conformal perturbation theory, preserve the 2,2 supersymmetry. So this come from, I'll just say this in words, come from weight 1/2, 1/2 superconformal primaries. Just like the marginal deformations of a bosonic, the ordinary standard bosonic CFT come from a weight 1,1 Virasoro primary. Marginal deformations in this case implies that they're exactly marginal. Namely, there's actually a family, at least a one-parameter family of theories that you can obtain by turning on a finite amount of deformation, exactly marginal. That's a rather non-trivial statement. This was first proven by Lance Dixon in the mid-80s. The argument was somewhat convoluted, actually. The argument basically amounts to saying that we can think of this as a part of the worldsheet theory of a superstring theory, and the potential obstruction to exact marginality have to do with scalar potentials, which can be recast as zero momentum limit or tree-level string scattering amplitudes. And from that, by playing with some SUSY word identity, he managed to prove this marginality. But the proof actually only proves that this deformation preserved n equals 1 superconformal symmetry. So that even that convoluted proof was not strictly speaking complete, but it seems to be accepted for many years. There's a much more simplified argument that was made based on some kind of spurion type arguments in a much more recent paper by Green, Komorgowski, Tajikawa, and Seiberg. And if you want to understand why this is true, you can study that paper, which actually makes much more general statements. OK, so but this is basically the reason why we have large families of 2,2 superconformal theory, because you can deform these theories exactly marginally. So you produce some family of CFTs on each point in this family. There's a different CFT. OK. And this is also the class of examples that this is also a way to produce a standard class of examples of compact irrational conformal field theories. So here, actually, the Narain lattice construction allows one to construct some irrational conformal field theory, because if you think of compact bosons, you can take some irrational radii for different compact bosons, and that generally will give rise to primaries of irrational weights. So that would be a class of examples of irrational CFT, but that's a cheap class of examples. We're still working with free theories. If you're asking for a non-free irrational compact conformal field theory, then this is really the only class of known robust constructions. So at a generic point on the moduli space of a Calabi-Yau model, it's expected that the CFT is an irrational one. And it's, of course, expected that the generic CFT should be an irrational CFT, because these ones all have actual conserved currents, higher spin conserved currents. One would think that generic CFT should not have such property. But of course, here, they still have this actual supersymmetry, which is still give rise to actual conserved currents if you want to view this as them as a bosonic CFT. And by the way, as I already mentioned before, even though the supercurrents themselves have half an integer spin, there's a way to produce a strictly modular invariant theory given this kind of spectrum by the so-called GSO projection. But anyway, it's a story that I won't have time to discuss in detail. I just want to mention one other class of important examples of superconformal field theories, which is a subset of this, in fact. That is 4,4 superconformal field theory. Now, there are different kinds of n equals 4 superconformal algebra. I want to focus on the so-called small n equals 4 superconformal algebra. These have the property that there are 4 spin 3½ currents and SU2 R symmetry current algebra. So an example of this would be some SUSY nonlinear signal model on hyperkähler target space, like K3 surface and its higher dimensional analogs, hyperkähler manifold. Let's see. I just want to mention that this includes the example of the so-called D1, D5 CFT, which is a particularly rich class of superconformal theory that exhibits all kinds of interesting behavior. And at some point in the moduli space of such theories, they made holographic dual as string theory, type 2 string theory on ADS3 times S3 times a 4 manifold, which is either K3 surface or T4. Okay, just a few more comments on the superconformal theories. Now, we know it's relatively easy to establish the existence of such theories and their moduli space. We know a lot about what kind of deformation is allowed, and we know something about the BPS operators in such theories that belong to shortened representations of the superconformal algebra. In other words, there are null states among superconformal descendants of the BPS operators. We know some things about the OP coefficients of BPS operators. But that's basically the extent to which we understand these superconformal theories. There's hardly anything precise that is known about the non-BPS operator spectrum and their operator and their, say, OP coefficients. And so this, we understand well, the non-BPS sector, there's not nearly as much as known, and so far the only reasonably useful way to probe the non-BPS sector will be based on either conformal perturbation theory, which is incredibly hard to work with in practice, or conformal bootstrap. Okay. Let's see. Now that's about it as far as kind of exact construction of conformal field theories that I'm aware of in 2 dimensions. Now there are, of course, in higher dimensions, we are used to the idea that you can produce conformal fixed points by studying RG flows. So you can ask, in 2 dimensions, we can maybe study some RG flows and find interesting fixed points. Now, you can start with some CFT in the UV and turn on some relevant operator and flow to some IR fixed point. Now, in higher dimensions, actually, especially if you are familiar with supersymmetric field theories, there are 2 different ways to generate RG flows, either by turning on relevant operator or by turning on a web and move. If there happen to be a moduli space of vacua. In 2D, there is no moduli space of vacua, and there's only this possibility. But if you want to really follow the RG flow and find the IR fixed point, that requires going beyond conformal perturbation theory. So this is typically, if you just hand me a CFT and hand me a relevant operator and ask if I turn on this operator, where does it flow to? It's a strong coupling question that's generally hard to answer. So unless it's protected by some symmetry, it's a little hard to control the endpoint of this RG flow. There are roughly, I would say, 3 class of examples where this RG flow is under some control that I'm aware of. One is the class of integrable RG flows. For example, it's possible to deform the minimal model by some relevant operator, and it could flow to either another CFT or flow to massive theory in IR. If the RG flow is integrable, then in the infrared you have some massive particles, but their scattering is completely factorized in the sense that the particle numbers are conserved and the set of momenta are also conserved. There's no particle production this kind of scattering. In this case, one can solve exactly the entire integrable RG flow and say determine the UV CFT given the information of the IR. But these are, anyway, these are, all the known examples are flaws among the known theories. So it doesn't teach us anything new about CFT themselves. And then there are the so-called Landau-Ginzburg models. In the bosonic case, they give rise to IR fixed points that are Neo models in the case of one field. I don't know the status of bosonic Landau-Ginzburg model with more than one field. Not sure what's known about the IR fixed points. In the supersymmetric case, in 2,2 case, there are abundant examples, and because of supersymmetry normalization property, they give rise to abundant examples of 2,2 superconformal theories. Some of which are related to Calabi-Yau models, but most of them are not. Most of them are more general. And then there are also some controlled examples of short RG flows. These are a little bit similar to critical vector models in 3 dimensions, say. As an example, you can take n copies of, let's say, n copies of the C equals 4/5 3-state Potts model. This is one of the examples of Neo models, actually not the diagonal module. Let me just say that, comment on that, this is not the Neo model defined by the diagonal modular invariant, but by a off-diagonal modular invariant. And in any case, in this,
that's the honest Potts.
Yeah, the honest Potts model. So this model has some Z3 symmetry, and there's some energy operator epsilon I. So there are, if you impose these Z3 symmetries, it turns out that the only 2 relevant operators you can turn on of this form, where I represent the copy of the n copies, and you can take the energy operator or their products. This turned out to be a dimension. So this guy has dimension 4/5. This one has dimension 8/5, which is still relevant. If you fine-tune the coefficient of this, this relevant operator generates an RG flow to some IR fixed point. So this is very similar to the critical OM model in 3 dimensions, in the sense that this looks like a double trace operator. So this RG flow turned out to be short, in the sense that, let's say in the n equals 3 case, it's known by conformal perturbation theory calculation that the UV, of course, the CUV is equal to 2.4, which is 3 times 4/5. And the IR fixed point, this computation based on conformal perturbation theory as well as Monte Carlo, that's about 2.38. So now it seems to be there's substantial evidence that this is a robust CFT, a new CFT in IR with some operator spectrum that one can calculate. The question is it new? Is it one of these classes? Actually, it's hard to tell. So I don't actually know. I don't think anyone has checked really carefully whether this falls into the class of rational CFTs you can construct by coset in this neighborhood, or is it a new irrational CFT? That's still a question. I mean, I've only seen a couple papers on this on the condensed matter archive, so it's not a particularly well-known.
But there is some kind of lattice formulation.
There's a lattice formulation of this. This is called the coupled Potts model. Yes?
Why the opposite for that? I mean, how would someone think through?
You mean this RG flow? Oh, I mean, the Potts model is a minimum model. It's one of the basic building blocks. It's natural to consider several copies and to try to couple them. And this way of turning out this deformation will be kind of trivial, because each one by itself will just flow to some massive theory in IR. But this one will couple different copies. So if you want to couple a bunch of Potts models together, this is a natural way to do it that preserve all the symmetries. Oh, no, it's not because lucky. There's a 1/n expansion. So you can understand the reason it's short from 1/n expansion. Apparently, n equals 3 is large enough.
But also this operator is not too far from our operator.
That's right. That's right. Yeah, there's ways to understand this. OK, so I think my half hour is up already. I just want to, OK, let me just, I will not even try to write anything. I just want to comment on the strategy of moving forward and trying to understand the landscape of 2D conformal field theories. If you look at this list of the known examples I've discussed, I mean, Of course, if you know anything that does not fall into the list, we can discuss in the discussion. You see, the majority, you think that the generic 2D conformal field theory should have no extra symmetry beyond Virasoro. In fact, a precise way to characterize this is one precise way to characterize this is the twist gap. The twist gap is a statement that the dimension of the operator of primary is this, and the spin is h minus h tilde by definition. The twist is defined to be dimension minus spin, which of course is the negative for 2D CFT, for primaries in the 2D CFT. So if you have a primary operator whose twist is equal to 0, it's necessarily a conserved current in the unitary CFT. So if there are no conserved currents, the twist of the operator will be non-zero. Now you can ask, apart from the vacuum, the identity operator, which obviously has twist 0 by definition, could there be a gap in the twist of all primary operators? Could there be, if you look at all possible values of the twist in the theory, could it be that all the operators have twist above some gap? Let's call it tau 0, the minimal twist. Now, from modular invariance in the simple analysis, which I will not have time to explain in detail, one can show that the twist gap, call this the twist gap, tau gap, is bounded from above in the compact CFT. So this for, I guess this is actually true more generally, by c minus 1 over 12 for c greater than 1. So this follows from modular invariance. But now, if you okay, so you and we don't know any argument to suggest anything stronger than this. But if you look through the list I've discussed so far, actually, all the compact theories we have with explicit constructions, apart from this guy here, which we don't really know too much about, they all have twist gap 0, and furthermore, they have extra conserved higher spin currents. So, for example, the free theory and their orbitals all have conserved higher spin currents, so are the rational CFTs. And the supersymmetric ones, they also have conserved, actually higher spin conserved currents from the super extended super Virasoro algebra. So that's somewhat bizarre because it's, while we know that this upper bound on the twist gap, actually there are no examples realized in non-zero twist gap. So that's just one example that indicates our complete ignorance about 2D CFTs. Either we're missing some very non-trivial constraints on the theory, or it's just that most of 2D CFTs will just have no idea how to describe them. And just one last thing I wanted to mention is that the way to approach general 2D CFTs, as I alluded to at the beginning, was to analyze the complete set of consistent condition that includes crossing of the sphere 4-point function, which is equivalent to the associativity of OPE, and the modular invariance of the torus 1-point function. Now, these can be analyzed separately, but in principle, one needs to combine both these together to get stronger constraints on the CFT. And it's hard to do directly. There's a slightly clever way to do this, at least partially combine sort of the information from both the crossing equation on the sphere as well as the modular invariance of torus 1-point function, which is to study the modular invariance of the genus 2 partition function of the CFT. Because if you look at this guy, it's you can think of it as a sphere with four operators inserted, and identify these two and identify these two. So that would already encode the modular invariance of the genus 2 partition function would already encode the sphere crossing equation in the case when two pairs of operators are identified. Or you can decompose this in another channel, view this as sort of two, let's say, tori are glued together by inserting one operator over here, one over here, and sum over all intermediate operators. So the modular invariance of genus 2 also knows about the modular invariance torus 1-point function. So by analyzing this, one can obtain some stronger constraints that will be hard to obtain by directly combining these two. And that is still a subject of, of current research, and we're trying to figure out how to do this systematically. Recently, we figured out how to compute systematically Virasoro conformal blocks for genus 2 Riemann surface. And the next step is to figure out how to extract the non-trivial constraints on the operator spectrum and OP coefficients of a general CFT based on this. So I should probably close here.
Thanks a lot for really comprehensive talks. Yeah, it's amazing how much we don't know about CFT. I have a lot to do. So I wonder if maybe we should just go. You can ask three questions during this panel, but we. Maybe first I'll just start with see if someone is following his lecture. Probably there are some questions.
So you gave us a nice overview of how much you can give us like a short summary of how much is known, how many tools, what's known about them, things which have relative role
That's a great question. So the best known example is the D1, D5 CFT. Okay, the D1, D5 CFT, but the life is not so simple. So D1, D5 CFT based, well, they come in two types. There's the one based on K3 and one based on T4. So at some point in the modular space, they have the description as symmetric product. At some other point in the modular space, they have description as a linear sigma model on the instanton modular space, Yang-Mills instanton modular space on K3 or on T4. So these are limits where we can understand directly from the CFT point of view. But unfortunately, in neither of these points, we understand the gravity side very well because they correspond to some very stringy regime on the gravity side. So we believe that in some parts in the modular space, the gravity side would be, string theory, will be described as a weakly coupled string theory on ADS3 times S3 times K3 or times D4. Now, there are special points in the modular space where the string theory is solvable on the worldsheet. That's the pure NS-NS frame. But unfortunately, that point also corresponds to a singular limit on the CFT modular space, where the spectrum becomes degenerate. So there's something you can do to try to match those two sides, but again, the usual problem is whenever you can understand the bulk, you have trouble solving the boundary theory. And apart from this, there's really not very much. All the other examples are much less understood. This one is not really understood so well compared to, say, equals force Renormalization, but at least we'll understand the modular space and all that. Other examples are much more poorly understood. So let's start by reducing the number of supersymmetries. So we can have 4, so this is 4, 4. You can have 4, 0 theory, the so-called MSW CFT, which can be thought of as commodification of 2, 0 theory on 4-dimensional Kähler manifolds with appropriate twist. You can also think of it as a theory living on M5 rings wrapping divides in the Calabi-Yau threefold. That is supposed to be due to M theory on ADS 3 times S2 times Calabi-Yau threefold. But the CFT is understood much less. We know the center charge, and that's about it. We know something about some counting of some index, supersymmetric index of these CFTs, but that's about all we know. And then there are nice supergravity backgrounds involving ADS3. So there's things like ADS3 times S3 times S3 times S1, which is supposed to have large n equals 4 superconformal algebra. And there's a series of papers, in around 2004 by Gukov, Martinez, Strominger, and more, dedicated to study this theory. But at the end of the day, they still didn't find what the dual CFT is.
Is there any clue, like roughly what it might look like?
There was a proposal in their paper that suggests that a special case of this, the dual CFT, would be the symmetric product of n copies of a CFT I call S. This one is a C equals 3 CFT. That's just a single boson and full of free fermions. Single free fermions. And the claim is that this thing has a Z3 Z3 twist field as well as Z2 twist field, which is marginal. And they suggest that it should be exactly marginal and leads to this deformation. At some point, I tried to investigate this deformation, and didn't seem to be exactly marginal to me by direct computation in conformal perturbation theory. And I asked some of the authors of the paper, and the authors have forgotten about the details. And so it's, but maybe same cannot be said for every author, but a subset of the author. So the status of that is not so clear. And even in that paper, they only proposed this for some very special case and not more generally. So.
Yeah, just a kind of philosophical comment. A surprising thing about these ADS3 CFT2 dualities is that, like, say, the D1. If you ask someone before 1995, what can you name a two-dimensional CFT? They wouldn't name the D1, D5 system, right? I mean, it's something a bit bizarre and esoteric. We know lots of 2D CFTs. So there seems to be, like, the ones that we know well, and all these, like, WZW models, we don't understand their gravity duals so well. I mean, the situation is quite different, for example, in ADS5, because if you ask someone before even 1995, can you name a conformal field theory in 4 dimensions? Most people would say n equal 4 super Yang-Mills. That was somehow the canonical example, even before all this wave. And somehow that immediately met with the gravity dual. But in 2D, we still haven't found something, it seems, right? I mean,
just from like very naive point of view, somehow you would expect it to be much simpler.
Exactly, yeah, but it turns out to be much more complicated. It somehow stands separate from higher D. And also, I mean, one should discuss, well, something that she's an expert on, these higher spin theories. So there are certainly these proposals on higher spin duals of certain coset theories. But they are a bit tricky too, right? There is some trickiness.
Right. So there was these WA minimum models in 2D, which are supposed to be built to. Well, I mean, the original proposal of Gabardine and Gabor-Kumar is that they are due to some version of Vasiliev theory in ADS3, coupled with some matter fields. But if you the full story is quite subtle. So. In that class of examples, that original proposal was essentially correct if you restrict to a subsector of the operator spectrum in the CFT, whose OPE close on its own perturbatively, right? Perturbatively 1 over n. So it only works perturbatively 1 over n. And if you want to make theory non-perturbatively well-defined, multi-dimensional, know that you have to include these additional sectors of the spectrum, which will give rise to a huge number of light operators in large n limits. And the dual is not quite just the simple Vasiliev theory. So that it was seen in that example that large n factorization does appear to hold, but up to some important subtlety having to these light operators. But that story is actually very much similar to the 3D Chern-Simons vector model on the torus, where you also have some huge degeneracy in the weak coupling in the large n limit of light states, which makes the dual potentially complicated. So it would be higher spin fields supplemented by some other sector. but we don't understand very well how they're coupled.
I see a question there.
Well, I'm not familiar with the paper, but I've heard the talk several times. Well, in higher dimensions, typically when you find some non-trivial RG flow pattern, you find a fixed point. Every time you find a new fixed point, you find a new CFT. In 2D, a lot of times when you play with these RG flows, you always end up with familiar fixed points. I mean, most of the time, as I was saying, you don't have a very good control of where the RG flow is going to, because it's a strong coupling problem, and it's. I mean, I don't have anything to say regarding this bifurcation. Yeah, I don't have anything to say.
I guess he was mainly worried about dangerous irrelevant operators that somehow. I think you always need the extra assumptions, right?
Yeah, I mean, this idea, in principle, sounds great if you know that the space where the RG flow lives on is a manifold, let's say. But often you'll have, often the flow doesn't go to some non-trivial fixed point, it goes to some massive theory or something. So which I guess from some point of view, you could say that
it pretty much always goes to massive.
Yeah.
Right? So you have to do tuning to.
Yeah, that's right. So the flow could lead to this space of couplings could have boundaries, where the theory becomes whether there's no or just kind of infinite ends where you just keep going and go to some massive theory. And also in 2D, there's a special thing that if you do perturbation theory, say with nonlinear single models, in the perturbed regime, there are infinitely many relevant coupling. That's another headache. I mean, that doesn't occur in higher dimensions.
Okay, are there any questions for Johanna, Daniel, maybe me?
There were a couple of them. I think there were just 4 people raising their hands.
I have a question.
Okay.
So I should be ask you give me a code form, and I want you to tell me what kind of codes are described Hilbert space of the field, and what kind of codes describe Hilbert space of the graviton. Can you give me such a code?
Well, I mean, the fields and the gravitons are coupled, so I'm not sure what you mean by trying to separate them. I mean, we can ask, does the bulk have dynamical gravity or does it not? I mean, in anything that's dual to a CFT, it will have dynamical gravity in the bulk.
Well, but I can discuss about different Hilbert space of the gravitons, some scalar fields.
Well, I mean, not really, right? Because the constraints of general relativity mix together the metric and the other fields. So the Hilbert space is some combination of both of them.
Yeah, but you don't. Looks to me that when you define it in codes, you didn't have constraint from general relativity at all. You just say, okay, I have the Hilbert dimension, and I just.
No, but well, it depends how you think about it. So, I mean, when I did the tensor networks, there weren't any constraints, but that was kind of a defect. That's what led to the area operator being a C number. So if we do, actual bulk, quantum gravity, bulk effective field theory, including the metric in the bulk, then we definitely are going to impose the constraints when we do that.
Is there a way to, is there an example how you
Well, I guess n equals 4 super Yang-Mills is an example.
So you find give a code for you.
N equals 4 is a code.
What's the type of structure?
No, codes don't necessarily have to have tensors. Those are special cases of codes. The CFT itself is a code.
It's just a very complicated
Yeah, it's just a very complicated code. I mean, these things, I mean, I hope you don't get the idea that the tensor networks are kind of fundamental in this story. The tensor networks are cartoons of what we think happens in the real story. You know, it's not like we think there's some, you know, right tensor network that's going to produce a controlled approximation to n equals 4 super Yang mills.
But what is the, so suppose you push tensor network to further, how far do you see it possibly improving to?
Well, it seems hard for me to get to understand how to
There's
think.
a lot of it people do numerically, right? Like,
Yeah.
so can you imagine some numerical approach that will teach us a lot?
Well, so far the numerical stuff has all worked in, you know, theories like transverse field Ising model where there's no large n.
And usually in one dimension. Right?
Yeah, usually in one dimension, practically, yeah. I mean, you know, in terms of, you know, just using them to try and study, you know, actual quantum field theories, prepare the ground state and so on. I mean, it's not inconceivable to me that eventually you could do, you know, more interesting theories like QCD or something using some version of tensor networks. But there you're sort of trying to solve a different problem. You're trying to, you know, represent, you know, the ground state of QCD or something.
They tend to have much easier time with gap theories, right? So maybe
yeah,
it
that's
teach
right.
us more about confining gravity duals or something like that.
Yeah, that's right.
But isn't it because the tensor is very simple in that case? Just, you know, the matrix product states.
Yeah, well, that's right. So roughly, I mean, tensor networks are really useful when the spatial entanglement is the most interesting property of the ground state. But, you know, when you have something like large N theory and there's a lot of stuff going on at sort of each point in space, then the tensor network isn't doing so much work for you. You know, you still somehow have to, I mean, somehow some of the excitement is now sort of going on within the tensors themselves. And you know, so when and then it's kind of, you know, you're sort of still having to work pretty hard, like to try and figure out what the tensors will be. So you know, yeah, I don't know.
Can I just ask you a question related to this? It's on. Okay, so so how does the large N limit tie into these tensor networks?
Yeah, so roughly speaking, you should think of, so each leg of the network you should think of as having sort of, well, the example I did was qubits, so it was 2 states, but it should really be more like e to the n, or actually e to the n squared states, like if you're trying to mock up, right, so then each of those legs that sticks out corresponds to n squared degrees of freedom. And so that you can do. The large n you can sort of do, you know, but the large lambda is the thing that actually is sort of hard to capture from the point of view of the
Wait, but
tensor network.
even without large n, if you just introduce this n states on each leg, does that already ensure large n factorization?
Yeah, but the problem is that so I think it does, but I think the problem is that the operator dimensions also generically grow with n. So if
that's the case, you cannot really unambiguously define large n factorization, right?
Yeah, that's right. So I guess that's what I'm saying.
I think large n factorization only applies to singlet operators. Right?
Yeah, that's right. So roughly speaking, so the challenge is then, so if you somehow, I mean, you somehow have to tune to try to get operators whose dimensions are order 1.
But
so
is there a formal argument that singlet operators obey large n factorization in this construction?
I think you can probably argue that. We'd have to ask, I mean, using random tensors. So the way it's usually done is the way you do the large n limit is at each tensor you choose independently a random unitary transformation, and then you average over all the unitaries. And then you can compute stuff. So that's what the Stanford group were doing. So basically they did the same network, or actually many more general networks too, but for example we could do that network and then put a random tensor with with n states running on each index, and then a lot of things work out nicely. I think you can see that the correlation functions are power law and so on, but with the random tensors they're power law with dimensions that grow with n. So somehow you would have to tune somehow to get something that doesn't grow with n. I mean, here it's sort of, in ordinary CFT you at least have the energy momentum tensor, right, whose dimension doesn't grow with n, but here we don't necessarily have something like that because we don't have a local theory on the boundary necessarily. We have some features of locality, but...
Sorry, I thought you want to build in locality by demanding Hamiltonian is local.
Yeah, that's right, but it's not, I mean, the Lorenz invariance is broken badly, though. For example, the rotation symmetry is broken to Z5 by that central tensor. So, yeah, I mean, somehow to get an energy momentum tensor, I don't know, you might have to tune or something. But I mean, I think there's a more basic problem here, which is that if you try to make the tensor network more dense in the bulk, like, to try and, like, achieve something that looks flat at distances that are small compared to the ADS radius, I mean, you're basically just turning it into like loop quantum gravity or something, right, which we know doesn't work. So I don't know. I mean, my personal bias is that it's a model that gets the ADS scale physics right, and somehow, we're going to need to, just having generic, perfect tensors or random tensors or something, we're not going to get this, this more detailed features.
As a general comment, I think we should lose fear about lambda of order 1, because it's I sort of tried to say it in my lectures, but lambda of order 1 is a vastly more common behavior than pushing lambda to infinity. Like, I would call the latter like an accidental, exotic, wonderful limit. That's why we learn to believe in ADS-CFT, but to be able to really learn more from it, we have to learn about theories which are not strongly coupled like that. So.
I have one question. Can you actually build a gravity dual tensor network for the Ising model or something like this? I mean, to just get some concrete example.
I mean, yeah, so for the Ising model, people are pretty good at making,
But that's very low end, right?
Yeah, it's very
low
low
end.
end.
To be,
yeah.
I'd like to learn how to do it for some, like, n copies of Ising model, maybe, or something like that.
Yeah, I don't know. Yeah, so certainly, yeah, like things where there's, a few degrees of freedom per site, that's what these, the real tensor network people are pretty good at. I'm a fake tensor network person, I don't actually write computer code and, try and find the ground state. But that's what the real people do. And for the Ising model, they can certainly do it. But I should comment that they're just trying to find one state. So, I had all these dangling legs in the bulk. I was trying to get this whole subspace. That's not what they do. They don't have any dangling legs in the bulk. They just have the network, and then it prepares one state at the boundary. And then you just play with the tensors to try and get the state that you want. And that's also a bit easier, because now you're not trying to get bulk effective field theory. You're just trying to find the ground state.
Can I invite some... If there are very basic questions about ADS-CFT, maybe it's a good time to ask without any fear, or because that was a lot of lectures were on that this week, or everyone knows this already. There was, yeah. Can you start with the base? Okay, it's fine.
Thought about Eric Verlinde's proposal to the degree to which it says something about
Is this being recorded? That's yes? Oh boy. All right, well, then I'll just tell you what I told Eric Verlinde. How's that? Yeah, I mean, I'm pretty skeptical, I mean, so I guess people have probably heard about it.
Well, I think you should just summarize in 2 sentences.
I mean, yeah, he's trying to, use holography to motivate some theory of dark matter. So basically the idea is you have n by n matrices, and you can split it into sort of a small block and a big sub-block, and the small block is describing standard model and particle physics and whatever, and the big block is describing the excitations of de Sitter space. The
this
de
will
Sitter
be
horizon.
the shortest lecture series.
And then what he wants to say is that the off-diagonal blocks correspond to dark matter. Okay, that's what he says. And then he says that predicts the deviations from Newton's potential, which can be checked experimentally and try to reproduce, rotation curves of galaxies and so on. Yeah, I mean, well, we could discuss whether or not it actually fits the data, but that's not my expertise, so let's not discuss that. So conceptually, I mean, I think the biggest problem with this argument is that, I mean, this set of words about the matrices and so on, I mean, we like those words, but I mean, we say them also in ADS. And there we think that what we get is just ordinary supergravity in the IR. We don't think that there's some mysterious dark matter that's not part of supergravity that's floating around. So to pin him down on this, I asked him, say you have a big ADS black hole sitting in the bulk, big ADS radius sized, and then orbiting that black hole, you have a copy of the solar system. So in that solar system, will you see deviations from Newtonian gravity? And he says yes. So I guess I'm skeptical, because I would have said that that solar system physics is described by supergravity without any extra dark matter. And so why should it be different in de Sitter space? I don't see any reason for it to be. And it's not like he really computed it. There's some sort of hand-waving and some plausibility arguments, and then somehow this formula appears. But yeah, I don't know. In the cases where we can actually study the formula, in n equals 4, it seems that it's just supergravity. So, okay.
There's a more straightforward analog of this, which is the BFSS matrix quantum mechanics, where you literally have MI matrices you can talk about the state described by this, by this block diagonal thing. In that case, in the holographic dual, if you are in a type 2A frame, then these single eigenvalues are D0 branes, and the rest, if they're still in the ground state, describe this some geometry with some Renormalization fields. And the off-angle stuff, basically that's what, it's part of, when you integrate that's part of what creates the space-time as seen by the zero branes. So, and we understand that should be described by supergravity.
I should make at least one phenomenological comment, sorry, also. So dark matter doesn't just explain galactic rotation curves, it's essential to the entire history of the universe.
Yes,
so you can't just explain.
Apparently people tell me that CMB pinned it down to many sigma.
Yeah, that's right. So for example, for the CMB, if you screw up dark matter, it's just you're totally screwed.
Some peak number 3 or 4 just would not look like this at all without.
That's right. Yeah. So for his version of things, since the dark matter is coming from the cosmological constant today, it would just be totally irrelevant during the early universe, and then the whole expansion history of the universe would be different. So if you ask him this, he says, well, I don't know. I haven't thought about that yet. So
let me make another attempt to get questions on some of the lecture series. Yes, yeah.
It's sort of related to the point you made about where the stars, and also just to clarify the geometry. Is there a maximally, is this a black break geometry that we
Yeah, that's the confusing question to which there were several answers. Actually, yeah, the special thing about the D3 brane system is, unlike the other brane systems, is that the metric is completely non-singular. So it's a solution of source-free supergravity equations. There are no, there are some other solutions where there are delta function sources. This is not one of them. So there are no branes located anywhere in the 3-brane space-time. If you write down this 3-brane metric that I wrote down and Johanna wrote down with the warp factor 1 plus L to the 4 over R to the 4, one tempting answer is the D branes are at R equals 0. No, they're not at R equals 0. The other question is, they're at R equal infinity. They're certainly not at R equal infinity. Then Oliver said something intriguing, they're everywhere. That is, in some sense, in the end, okay. But specifically, I'll tell you why this is okay. There are certainly no D3 branes in that space-time. So you think of that as replacing the n equal 4. So the closest thing, I think, is that the branes are at R to the 4 equal to minus L to the 4. So they're somewhere at complex R, but they're not visible in this space-time. So you're just supposed to think about the branes are nowhere to be seen. This throat replaces the low-energy dynamics of open strings. But then maybe I should let Johanna comment on this.
What is your argument why the branes are not at R equal to 0? So I mean,
because there is no source there. If they were at R, if they were at R equals 0, there would be a delta function source there, and you see that the Einstein equations are satisfied without this source. Like you can compute. So r equals 0 goes off to infinity, basically, right? So there is no.
So there's not this naive picture that you have a soliton and there's this subspace in the 0, 1, 2, 3 directions which is preserved by the supergravity solution.
Well, it's a solution that carries exactly the same flux as three branes do. But you don't see the source of this flux. The flux is just coming in from somewhere, but you don't see that somewhere. So it replaces, I would say, the D3 branes in this. The solution is complete without any sources, and you're supposed to think of this as replacing the three branes.
Okay. So, I mean, one thing I wanted to add maybe is, again, to repeat this issue about the low energies. I mean, it's really, I mean, the motivation of the ADS-CFT correspondence for the D3 branes is really that in both low energy limits, you have flat 10-dimensional space where you expand gravity to quadratic order in the fluctuation, so it doesn't interact really. And on top of that, then you have some other lower energy degrees of freedom, which in one particular, on the one side of the correspondence, it's NX4 super young Mills, on the other side, it's the fluctuations in this road. And so then the idea is if you have flat 10D space free on each side, then you should also identify this road with this NX4 theory.
I think there is some very concrete comment that, like when people were originally, like there was this Horowitz-Strominger solution for the near extreme O3 brane. They used a somewhat different radial coordinate. And that radial coordinate actually was related by a shift of r to the 4. So in that radial coordinate, I think they were sitting at r equals 0. Yeah, I don't know if I can on the fly reproduce this, but I think there was. So when we say that the work factor is h is 1 plus L to the 4 divided by r to the 4, right? You can write this as r to the 4 plus L to the 4 over r to the 4, right? But there was some other radial coordinate which looked like you were basically just shifting this by L to the 4. So my recollection is that it may be okay to say that the D3 branes are in these coordinates at r to the 4 equal to minus L to the 4, whatever this means.
Well, maybe I'll make a comment on that also. So so this L that Igor wrote is really G times alpha prime. So this idea that a D brane is a thing that's somewhere is based on a perturbative definition of the D brane, which is that it's a point where strings end. Okay, but in perturbation theory, G times alpha prime is 0. So this whole region where the geometry is changing has size G times alpha prime, and so in perturbation theory, it's just the whole region is collapsed down to 0 size. So this whole right. So and that's the sense in which the D brane is somewhere. But once you are working non-perturbatively, right? Then then the D brane, it's not just a place where a string ends. It gets fattened out into this whole geometry.
Somehow, as you're cranking up G string n from a very so you're supposed to trust the D3 brane picture at very small G string n, right? Then the back reaction on space-time is small, and in that limit, as Dan said, it all collapses. And you just see three branes surrounded by flat space. Then, as you crank up G string n, that somehow magically expands into this throat, this semi-infinite throat, this ADS. And we don't have a proof of it, but there is this argument based on essentially comparing the D3 brane stack. But maybe Johanna wants to.
Yeah. Okay. So. Just to emphasize this again, I mean, so first when I talked about the open string picture, we were in this limit where GS times n is very small. And then you can have this perturbative picture where the brane is localized. And then this whole discussion on the gravity side was in the limit where GS times n is very big. And then now we just argued that's where it becomes. So then you're in a non-perturbative regime, and it's much harder to visualize the brainers. some localized object. It's the entire supergravity solution. But then the idea is to take this near horizon, I mean, this low energy limit on both sides. So the limit is really that alpha prime goes to 0, but you keep all the length scales fixed. And the second part of keeping all the length scales fixed is extremely important in taking this limit. And yeah, and then the conjecture is to identify the two low energy limits in the two regimes. So you mean at finer temperature? Yeah.
Yeah, R equals 0 is the horizon, and the branes are somewhere behind the horizon, not there. Or whatever.
But okay, I guess this is. I mean, so Igor has been working a long time on this, so maybe we should. I mean, you should ask you. I mean, so if you just look at these three branes at 0 temperature, so can you expand on this this analogy to black holes, and so why was this word horizon used? And
well, I think it's like an extremal black hole horizon.
It is a horizon. It's Poincare horizon.
It just becomes the Poincare horizon in ADS.
Yeah, I would like to offer an explanation of exactly where the brain is sitting at.
Okay.
So you can't see m branes at the same time here because they're strongly coupled. Or you can see individual branes if you move them off the others.
Right.
So you can peel off one brane away from the remaining n-1 branes. And that corresponds to, if you work on the Poincare patch of the ADS, where you have this Poincare horizon corresponding to R equals 0, that corresponds to n equals 4 supermills in Minkowski space. But in the conformal invariant vacuum, you can n equals 4 supermills has a moduli space of vacua, so you can move off to a conformal symmetry breaking vacuum where the gauge symmetry is broken to let's say u n-1 times u1, and that precisely corresponds to moving a single D3 brane out of the horizon. And then in that case, you'll really see a brane just sitting outside the horizon at some small r.
But that also makes it clearer why you don't really see the n branes, right? You've peeled one, and then you'll just see D3 brane and ADS 5. But the bulk n branes you don't see. Yeah, I mean, this peeling off of a brane is an extremely useful thing for studying Wilson loops and all sorts. Yeah, the confusing thing is that people often say that the gauge theory lives at the boundary, in the sense that you compare at the boundary the
that's the next step. So this is just an argument which is natural once you asymptotically solve your equations of motion in EDS space near the boundary, because then you have this nice interpretation of the boundary and the source in the VEV, and then of course it's very natural to think of your theory being located at the boundary, but I agree this doesn't really follow from the D3 brane picture.
Yeah, certainly not. The n branes don't sit at the boundary. Sometimes it's convenient to put this probe brane at the boundary to study Wilson loops.
Yeah, no, I think it's true. The branes are everywhere. I mean, actually, Eva Silverstein, maybe some of you know, this is like one of her biggest pet peeves. Every time someone says the boundary, the CFT at the boundary, she has to interrupt and say,
well,
no,
we used to complain about this, because I mean the reason, because I always thought that the branes left the building and you are still have this throat, but the reason that the gauge theory is everywhere is because the radial coordinate is the energy scale in the gauge theory. So in that sense, you're really seeing the full RG.
Yeah, but okay, so there I have a question. I mean, I agree it's very natural to assume that, so your radial direction is the RG scale, and the boundary in the UV, and in the interior in the infrared. But certainly, I think what you can't really do is to have a foliation of, say, 4-dimensional spaces, which correspond to the same CFT at a different scale. I mean, this maybe works for the UV and the IR fixed points, but along the scale, I don't think this is
it's
so
some
easy
kind of definition of RG scale. It may be a bit tricky to decide from the field theory point of view, but it's still like we definitely see some correspondence.
Yeah, I mean, I think this is the thing that was made precise by what I was talking about, right? I mean, you have an operator, and depending on where it is in the bulk, its spatial support is big or small in the boundary CFT.
Okay.
But they're all in the same boundary CFT on the same Hilbert space.
Okay, yeah, that's a good point.
Yeah, I would say that even though this is not the proof, clearly this D3 brane system is an incredibly serendipitous thing, which made everyone believe in ADS CFT, because even though the argument is still not completely rigorous, because you have to track from small G string n, where the back reaction is small, to large G string n, where you carve out this sort of low curved throat. But because of this maximal superconformal invariance, somehow this is a mild operation. So cranking up G string n can really I mean, that's where the proof should lie, but we now have tremendous evidence that it works.
I mean, I think it's basically rigorous. I think the only thing you need to assume is that n equals 4 super Yang Mills is the only quantum field theory with that amount of supersymmetry in those symmetries.
Which it obviously is.
Which we think it obviously is, right? I mean, I don't know. That we have, I guess in principle we need to use the bootstrap to prove that or whatever. Like there could be some non-Lagrangian n equals 4 theory. But it seems to me like that's the only loophole.
Well, but that, I would say that's on more solid footing than the non-perturbative existence of type 2B string theory.
Oh, no, sure. But we're assuming, fine. But no, but I mean, we're assuming that string theory and D-branes, these things make sense.
How do you know there's a unique non-perturbative completion?
Yeah.
No, sorry. The proof starts from assuming that string theory in 10 dimensions makes sense. And then you take the D-branes, you say at low energies, gravity decouples because it's irrelevant interaction. And so then you have left some quantum field theory on the branes. It has n equals 4 supersymmetry. It has the symmetries of n equals 4 super Yang Mills. What has the moduli space with gauge group UN or SUN? I mean, what else can it be, right? I mean, that's
well, okay, but how about the strongest?
The amazing thing in practice is not just that the two theories are dual to each other, but you really know how to compare precisely what you mean by coupling on one side to the coupling on the other side.
Sure, yeah.
Because initially people thought, oh, you will never check this, because by the time you have cranked up lambda to be large, how do you know that it's not lambda, it's lambda and not what we would call lambda squared or something like that. And all these worries kind of went away when the integrability people cranked it all out.
Okay, but so this is my question. I mean, so I guess your argument still applies for the weak form of the correspondence. I mean, how would you prove ADS-CFT for all n?
I don't even know how to think about the weak form.
What is the weak form?
The weak form is when n is infinity and lambda is large and fixed.
Sorry, but the proof I gave works for finite n and finite lambda, so doesn't that just prove it, period?
I
mean, not I gave, Maldacena gave, sorry.
Actually, I have a hard time thinking about only the strong lambda limit, right? To me, certainly the large n limit is very important because it separates quantum gravity effect, and who knows what quantum gravity is, you know. But in the 12th large n limit, you have to think about the whole range of lambda, right? Spanning it from small lambda where back reaction is small and you have the perturbative Yang Mills.
Okay, but for a full proof, wouldn't you have to quantize gravity in ADS 5 times S5 spaces? I mean,
well, I think that's then once we get control of 1/n corrections, that will teach us how to fully quantize gravity.
It's great that you also sound so optimistic that we get something.
No, but it's clearly something is working very well. So far we have few concrete 1/n results, but that.
I mean, I think you do have, like she said, you do have to assume that type 2B string theory is a thing.
Okay, I don't assume that.
So yeah, and if you don't assume, right, I mean, if you don't assume that, then, you know, I don't know. Then I think you're actually led to the point of view which I said, which is that then you just say that the gauge theory defines the quantum gravity. And then you can do checks that are consistent with that notion.
Since we're running out of time, maybe each...
I have another basic
okay.
I thought there was like a subtlety in this argument with these three branes. I thought there was like a subtlety with like decoupling, that there's like an intermediate region between the throat and the...
but that's under the barrier region. That's
you mean like deciding whether the group is UN or SUN, that kind of thing?
No. I mean, if you...
subtlety with decoupling, that there's an intermediate region.
No.
And it's not, or that's a rigorous...
No, there's this huge barrier.
There is a huge barrier between the two, so nothing moves there. I mean, the decoupling works because you have to tunnel through this large barrier. Like if you just write down the equation, say for the dilaton, you see this barrier, and at low energies it gets impenetrable. So,
right. I mean,
so the decoupling is absolutely there.
And from the CFT side, it's even better because then you just have, conformal field theory coupled to gravity, and at low energies, gravity is irrelevant, no matter how strongly coupled to CFT.
I was going to ask each of the lecturers to just offer some parting comment, or I mean, I don't know. We could have one or two more questions if there is a. Okay.
Yeah, okay, so good. So that factorization I assumed in the CFT. So it's a general fact about, about gauge theories that it's true that some UV regularizations of gauge theories don't factorize, but other ones do factorize. So by modifying the theory in the UV, you can turn it into one that factorizes. And this is related to this question, this comment I made earlier, that whether you're a gauge theory or not is not a fundamental property of a CFT. So implicitly what I was doing there was I was at some very high energy scale, high compared to any bulk question we could possibly be interested in, I'm sewing in a little bit of extra UV physics to let the Hilbert space factorize. Now, in principle, I don't have to do that. I could have instead also treated the boundary algebraically and allowed for so instead of talking about factorizing the boundary Hilbert space, I could have just said I have the algebra of one boundary region and its commutant in the other region. And I think everything goes through. I didn't bother to generalize it to that because this decoupling argument convinced me.
Okay, I think just for time constraints, we have to probably wrap up.
There was one question there, maybe.
Really short one.
Mm-hmm.
When we use Witten diagrams to compute correlators, should we also think of that like the boundary properties?
No.
For the correlation part, you don't need to.
I mean,
No, there is nothing spilled off. It's a pure gauge theory in the conformal invariant state. And you are really, it's just a perturbative calculation with sources at the boundary of ADS. So you're using bulk.
the sources of the boundary of ADS as being exactly.
But they are. I mean, that was the whole point. That was the extrapolate dictionary. So, but peeling off a brane changes the theory.
Yeah.
The ground state is different. All the excitations are different. The Witten diagrams, I claim, in the version of the dictionary I like, are understood entirely as correlation functions in the CFT.
It's not in a broken
changes of the
state.
vacuum. Yeah.
To define the Wilson loop, you need to break conformal invariance to talk about this, the notion of charge in the fundamental representation.
The question was, in this sense, we still think of the discrete living at the boundary.
Well, we just identify the field theory quantities with asymptotic behavior of fields in ADS. But that computation refers to completely unbroken conformal state with absolutely nothing at the boundary. No probe brane.
I should add that the peeling off brane cannot be done in global ADS. It can only be done in Poincare ADS.
Exactly,
Global ADS
exactly.
due to Yamil's theory on the
Yeah,
sphere.
it wants to
there cannot be spontaneous breaking of
Mhm.
symmetry in a compact space.
Mhm.
If it's in flat Minkowski space, then you can.
Yeah, that's another reason. I mean, usually you work these calculations in Euclidean ADS asymptotic to S4, and there is no probe brane. Okay, maybe just each of us makes one comment, or...
Well, one comment
just
is
to
I
wrap
really
up.
like teaching here, and it was super fun, and it was great when you asked so many questions, and I really enjoyed that, and I hope you enjoyed it too. And now I'm motivated to read more about these things. I mean, I realized that in 5 times 75 minutes, you can only cover very little if you really aim at explaining in such a way that it can be understood. And there are huge amounts of things I really wanted to say and had no time to. So, well, I mean, even if you already look at the TASI wiki, I put my lecture notes, and you can see they are double as long as what I actually managed to say. So maybe you have some interest in having another look there. Anyway, thanks a lot, and good luck to all of you.
Okay. So I want to second that. It's been a lot of fun being here with all of you, also with the organizers, the other lecturers. it's always fun to try to present things to a new audience and have them try and drill holes in what you say. So yeah, I don't know. I guess I also wish you the best of luck. Make sure to have fun. I know I asked that guy that depressing question, but don't worry too much about these things. It's doing a PhD in physics is a lot of fun, and there are lots of options afterwards. And either way, it's a good thing to do. So you get to think about cool stuff. You don't have to be at work at 9 in the morning. So enjoy it.
That is a really amazing life. Come to think about it.
Well, I'll still be around next week, so I'll come to some lectures so we can discuss physics. I'll spend the rest of my time climbing. And
yeah, I'm not saying goodbye, and I'll be around next week. First, I want to thank the 3 real lecturers who gave series of talks and really did a great job. Thank you very much, and I hope we conveyed how much we don't understand. So your generation has a big role to play, and there are many problems which, like, you always think everything is known, but we only understand special limits or some particularly easy calculations, and there's a lot left to do. So I hope you all work hard and step in. Okay, thanks. Sorry for running over.